we should be realists. We should be realists about quantum mechanics. I need to kill this. No, to do that, let's take this return.
Got it.
No, to do that.
It doesn't come up on your screen.
No, I don't know.
Oh, there you
Just try to desperately avoid touching leave meeting. Let's see. There we are. Okay. And I'll move this bar as well. I think if that goes to the bottom, it will get in the way of the slides less. Okay. Yeah, okay. So you'll typically see statements like, okay, there are almost as a throat clearing gesture in a bunch of literature. Well, yes, there are things we could do that are not realist. We're not going to do them because we're realist, because not being realist is bad. I actually think that's a really bad way of framing that part of the discussion, but it's not going to be my focus today. The second bit of the conventional wisdom goes, I'm still getting used to this computer, that there are basically three classes of realist solutions to the measurement problem. Invariable theories, exemplified by Bohm's theory, the Broglie-Bohm theory, dynamical collapse theories, exemplified by the GRW-Weber theory, and the Everett interpretation. And all of these are empirically equivalent. So here's a typical statement in this kind of literature. This is a recent paper by Dennis Dietz. The different interpretations of quantum mechanics that we've sketched, and I'm still getting different interpretations of quantum mechanics we've sketched can be taken to be empirically equivalent in a strong sense. No future macroscopic observations can be expected to be able to distinguish between. One sees statements of that kind fairly widely. As a corollary of this, the question about how to choose an interpretation of quantum mechanics among these realist options is a special case of something familiar in general to philosophers of science. It's a special case of the underdetermination of theory by evidence, the situation that we supposedly run into sometimes in science, where we have more than one theory, both of which are incompatible in some relevant sense, not the same theory, but make the same empirical predictions, and so can't be straightforwardly distinguished by some kind of empirical test. So, for instance, recent paper along these lines by Matthias Egg. Egg says, the choice between different quantum ontologies is underdetermined by the scientific evidence. Underdetermination occurs between the different responses to the measurement problem. These are sometimes called different interpretations of quantum mechanics, but it's more appropriate to view them as predictively equivalent rival theories, making this an instance of the well-known problem of underdetermination of theory by evidence. What I want to engage with in this seminar is going to be the second and third parts of those. It's going to be the thesis that underdetermination is the right way to think about the quantum measurement problem, and that the resources of underdetermination are relevant and appropriate for resolving the quantum measurement problem. What do I mean by them being relevant and appropriate? Well, here are some philosophical lessons that get drawn by philosophers from this kind of underdetermination framing of the problem. So the first point is a lesson that gets read back into general philosophy of science, supposedly from the philosophy of quantum mechanics. First lesson, underdetermination happens. It's real. It's not just a philosopher's fantasy. There are realistic physical theories such that we can't distinguish between them using the evidence. Here's Craig Callender on this recently. With these three research programs, and he means the three I listed before, it seems we face the realist nightmare. Many philosophers suspected that the threat of underdetermination is artificial, confined to excessive flights of imagination and not genuinely scientific theories. However, these three programs are neither philosophers' toys nor notational variants, and are clearly scientific in letter and spirit. Quantum underdetermination is the real deal. And just to say something briefly here to those of you who don't have a philosophy of science background, what he means by the realist nightmare here is that traditional scientific realism says sufficiently successful scientific theories are probably true, that the success of our best scientific theories is a reason to think that they're correct. And the threat from underdetermination to realism supposedly goes, if there are multiple such theories, then the inference from this theory works really well empirically to this theory is probably correct can't be true, because you'd end up making it multiple times to multiple incompatible theories. And you don't. So that's the first response, and that's a response in general philosophy of science. But there's also a response inside the debate about the measurement problem itself, which is that the kind of resources that philosophers have traditionally appealed to block the threat from underdetermination are the kind of resources we should be appealing to decide between interpretations of quantum mechanics. So typically philosophers of science have had two sorts of response to the underdetermination threat. One has been to deny it happens, which supposedly quantum mechanics is telling us we can't do. And the other is to say that there are so-called extra empirical virtues, advantages that scientific theories have beyond the barely predictive, which lead us to prefer one than another. So one sees appeals here to which theory is the simpler theory, which theory is more fruitful for the development of new physics, which theory is more explanatory, moves of this kind. You can make a case that a lot of these sort of come down to various different aspects of explanatory power. And so you can make a case that it's some kind of inference to the best explanation that's resolving the underdetermination. So in this case, the idea is that it's appeal to these extra empirical virtues that we're using to decide between these empirically equivalent interpretations of quantum mechanics, or really these empirically equivalent theories. So again, here's Paolo Acuna. I should say the reason I'm quoting fairly extensively to support this is that, just a spoiler alert, I think there's something really profoundly wrong with all of this way of thinking. And I just want to try to make reasonably clear that I'm not attacking a straw man here, that this really is quite a widespread position in the current literature. So here's Acuna, just this year. The predictive equivalence between quantum theories implies that a choice between them is underdetermined by the evidence. However, agnostics aside, both in physics and in philosophy of physics, there are several parties which defend one or other of these theories. So it's obvious that some philosophers and physicists do make a choice. Such a choice is based on non-empirical considerations. Pragmatic, epistemic, ontological, and metaphysical criteria are usually invoked in order to defend one interpretation of another. These non-empirical factors, though subject to controversy, are not arbitrary, which means that evidential underdetermination notwithstanding, a rationally supported choice between quantum theories can be made. And you can kind of see this way of doing things in a lot of ways the actual literature plays out. So for instance, maybe we choose on grounds of probability. Maybe we can't justify interpreting Everettian mod-squared amplitudes as probabilities, say critics of the Everett interpretation. No, we can justify that better in the non-Everett case. The Everett interpretation improves our philosophy of probability, say the defense of the Everett interpretation. Critics of Bohm's approach say the Bohm particles are epiphenomenal. They're not doing any work in the theory. They complicate the theory to no value. No, say advocates of the Bohm theory, the particles are what the phenomena supervene on, and that's the role they're playing. That's what we like. Extremely common to see appeal to Occam's razor here. Many worlds is a wildly extravagant ontology, say critics of many worlds. Many worlds is simpler than the alternatives, and Occam's razor is about simplicity, say defenders of many worlds. As David Deutsch puts it, the many worlds theory is cheap on assumptions, but expensive on universes, and we should aim to be cheap on assumptions. Maybe we want to say it's inelegant, it's empirically unjustified to add a platform to quantum mechanics. Maybe we say, no, collapse is what we need to understand the theory better. And here's a third philosopher's lesson from underdetermination, which I'll make less of, but I think is important, and flows more into the kind of general metaphysics of physics. If these are the kind of resources we're using to choose between interpretations of quantum mechanics, then the kind of game we're playing that's pretty similar to the kind of game metaphysicians are playing in the more sort of ontology-driven corners of metaphysics, where again we have underdetermination of theories, and where again it's an appeal to simplicity, to elegance, to explanatory strength that people tend to use in advocating one metaphysical theory or another of fundamental ontology or fundamental aspects of what relations or powers or concepts or laws might be. And so, the last 10 years, I'd say, has seen a real growth industry in what you might call the metaphysics of physics that's very much applying this kind of technology and ideas to decisions between, well, in particular, these three approaches to interpreting objects. That's how philosophers respond to underdetermination. Physicists have a slightly different response to underdetermination. Shut up and calculate. If really that's what's going on, if really we've got these empirically distant equivalent theories, and they just differ in these kind of rather ephemeral virtues, then it doesn't matter. Don't worry about it. Get on with doing actual things. Okay, so here's what I want to do in this talk. I'm firstly going to review the general ideas of underdetermination in philosophy of science to remind ourselves what's going on here and what the targets are. I'm then going to say a bit more sharply what I think the theories are on which between which we're deciding when we're considering this issue of underdetermination. And then I want to argue that under no sensible construal of what underdetermination theory by evidence is, can we say that there is meaningful underdetermination between these various approaches? And to give a nominal spoiler for something that I'm sure is fairly obvious from other comments that said, what I want to claim is that the dynamical collapse and hidden variable theories are not empirically equivalent rivals to Everett-style unitary quantum mechanics. Okay, so let me talk a bit about underdetermination in general in philosophy of science. And for some of you, this is a revision exercise of things you no doubt know well. So it's helpful to distinguish between strong and weak notions of underdetermination in philosophy of science. Strong underdetermination happens when, in principle, there is no experiment which distinguishes between two theories. It's not possible, no matter how advanced our technology might be, no matter how science fictional we allow our capacities to be, it's not possible to distinguish between the two things. There aren't any uncontroversial examples of strong underdetermination in philosophy of science. The examples that one could come up with relatively straightforwardly tend to be contrivances. They tend to be things like there are no unobservables, but everything appears as if there are unobservables. Or everything's as it is according to our normal physics, plus there's an invisible pink elephant sitting in that corner that doesn't interact with anything. Alternately, they tend to be things which are arguably notational variants. One candidate you might have for underdetermination is that there's underdetermination between a reading of general relativity in which gravity is the curvature of space-time and a reading of general relativity in which space-time is flat, but in which gravity is interpreted as a universal force or a spin-2 field interaction. These are cases where the mathematical formalism is the same, though, and there's at least a tempting response to say these are merely verbal differences, and ultimately we're still dealing with the same theory. At any rate, that kind of difference of the verbal interpretation of formalism is different from the kind of stronger idea that's mattering here of an underdetermination between formally inequivalent things. So that's strong underdetermination. Plausibly, it doesn't happen. And in fact, often quantum mechanics itself is the example given, as in Calendar's quote, of a counterexample to the claim it doesn't happen. Weak underdetermination happens when right now there's no experiment that can decisively, conclusively distinguish between the two theories. And underdetermination does happen. We can see relatively clear historical and present examples, and I'll illustrate briefly. So here's a current example: what killed the dinosaurs? We know an asteroid about the size of Manhattan Island hit the Earth 65 million years ago. We knew it originally because of the iridium spike between the Cretaceous and Tertiary in the fossil record. It's reasonably easy to see reasons why a Manhattan-sized asteroid hitting the Earth at orbital velocities might be bad for things that live on the planet. So it's highly plausible that it wiped out the dinosaurs. We also know that there was a tremendous period of excessive volcanism happening at the time, and the causal mechanisms by which the asteroid killed the dinosaurs and the evidence for that actually happening is a lot weaker than the evidence that the asteroid impact happened. So the sort of alternative volcanism theories of dinosaurs dying out are very much live, and all sorts of complex hybrids around the fact that it was just extremely bad luck to be a dinosaur at 65 million BC are also quite good. Here's a arguably slightly more historical example. This is, the jury's out to some degree. The debate between dark matter and MOND, or modifications of Newtonian dynamics. So we know, and we've known for decades, that if you look at the rotation curves of spiral galaxies, that is how fast things in spiral galaxies orbit as you go out through the galaxy, that the way they rotate, the rotation curve, doesn't fall off in the way you'd expect it to if you just did ordinary Newtonian gravity applied to the visible light in the spiral galaxies. It actually basically doesn't fall off at all or hardly at all. Spiral galaxies rotate almost as if rigid. And Newtonian gravity as applied to the matter we see doesn't explain that. And the discrepancy gets bigger as you look at larger and larger astrophysical contexts. It's more dramatic for the local group of galaxies than for individual galaxies. It's more dramatic for superclusters than for individual galactic clusters. And one account as to why that might be, the dominant account, is that the matter we see in the universe is not all the matter, but actually entirely leaving aside the dark energy that seems to be driving the expansion of the universe, then for every kilogram of ordinary luminous matter in the universe, there's about 5 kilograms of an unknown, we're not sure what it is, dark matter in the universe. But there's always been the rival idea that instead Newtonian gravity is wrong, or more accurately, Einsteinian gravity is wrong, and as a corollary of that, it's Newtonian limit is wrong. And these modifications of Newtonian dynamics have been advocated for decades as an alternative to the dark matter theory. Now, if you look at how that debate's played out in the last 20 years, then you find that to a very large extent, the astrophysical community has concluded that the dark matter is the right explanation here and that MOND is the wrong explanation here. So things like the bullet cluster, which seems to be a case where we've had a galactic collision and where your inferences as to where the mass is and where the light is, just from the directions in which things are falling, shows that the mass and the light in different days looks like relatively direct observational evidence for dark matter. And if you look at the distribution of irregularities in the cosmic microwave background, you find a distinctive spike in the kind of angular analysis of those that has a fairly clear explanation in the dark matter theory and is opaque, so to speak, in the MOND theory. So you now have a situation where the vast majority of the astrophysical community is pretty convinced that the dark matter theory is correct, and the small minority doing MOND are increasingly pursuing a fairly sort of lonely and isolated research trajectory. So would you call that underdetermination, or would you call it a past underdetermination? It's kind of a bit of a blurry boundary. It's definitely a case where, for the great majority of the community, the evidence is spoken, but it's not a place where you could say there's an utterly conclusive empirical refutation. Here's one more, even more historical case. Look at the question of Big Bang cosmology versus steady state cosmology. I mean, we're now basically totally certain that there was a Big Bang. And if you check the textbooks will say things like, well, when Penzias and Wilson discovered the cosmic microwave background radiation, then we knew the Big Bang theory was true, and the rival steady state theory, where the universe had existed forever but matter was constantly being created, is false. But even before Penzias and Wilson, there was a lot of evidence that seemed to push towards the Big Bang theory. And even after Penzias and Wilson, there was plenty of attempt by advocates of the steady state theory to push back and say, no, we can explain this, we can make sense of it. And that continued to happen for the successively developing more solid evidence. And so while right now, I think you can look at the evidence and say there is no underdetermination between the Big Bang theory and the steady state theory, it will be hard to point to the exact moment in the scientific record where that ceased to be the case. That's the case. Okay, that's my whistle-stop tour of underdetermination. Now let's do a whistle-stop tour of what the theories in quantum mechanics are that we're considering for which underdetermination applies, allegedly applies. So I want to set this up as follows. I want to distinguish between various different ways of doing quantum mechanics. And I'm using way in an intentionally loose style to avoid getting caught up in, am I talking about theories or interpretations or what have you. So the first way you might do quantum mechanics, and this is really a cluster of ways, is the modificatory way. You might change the quantum formalism and use different equations. So I'm not, for the sake of a talk, with this going to review dynamical collapse theories and hidden variable theories, but roughly speaking, dynamical collapse theories are going to modify the theory so that the unitary evolution of quantum mechanics breaks when systems get large enough or complex enough, and macroscopically indefinite superposition spontaneously and randomly collapse into one or other definite term. Hidden variable theories are going to say that while the quantum state does evolve unitarily, there are additional degrees of freedom, the eponymous variables, which are dynamically guided by the quantum wave function and whose task it is to pick out, or if you want, define or arguably constitute the ordinary definite macroscopically observed. So the modificatory way is really the modificatory several ways. Then there's what I call the decoherent way. Everything is unitary. The Schrödinger equation is all there is. I don't mean that ontologically, I mean all there is in the formalism of our theory. Lab processes are more physical processes. If we want to use quantum mechanics to model lab processes, we can. If we want to do complicated situations where it's kind of ambivalent, if you want to even say it's a measurement, that's not a problem. You just extend your quantum mechanics to cover that larger system. And if you want to understand why it is that we don't seem to be able to interpret the quantum state probabilistically at the microphysical level, but we can get away with doing it at the macroscopic level, appeal to decoherence theory. And then I think it's helpful to distinguish a third operational way, which is that the whole way we want to use quantum mechanics is that we prepare a system, we evolve it, and we measure it, and the preparation and the measurement are outside the scope of quantum mechanics and to be understood primitively or with appeal to some other theory, and only the evolution between preparation and measurement is to be understood inside the unitary formalism. But I'm not really going to talk about the operational way. So my target is going to be, for thinking about underdetermination here, that there's underdetermination between, firstly, the decoherent way, and secondly, one or more of the modificatory ways. So it's normal in this literature to more or less identify the decoherent way of doing quantum mechanics with the Everett interpretation of quantum mechanics. You know, I've argued at book length and beyond that that's the correct view, but I'm actually not going to touch or defend that in this in this talk. Insofar as there are multiple things that might deserve to be called interpretations of quantum mechanics, which at the formalism level are, can be identified in the decoherent way. Insofar as that's the case, nothing I'm going to say is going to touch on that. So for instance, it's plausible that the kind of relational approach to quantum mechanics that Carlo Rovelli champions could be put into the decoherent way. It's plausible that certain sorts of pragmatist or instrumentalist ways of understanding quantum mechanics at least aspire to be put into the decoherent way. And I'm not going to say anything about how those are to be distinguished by the evidence. It's possible there's a sort of related underdetermination way of talking about the selection there. I think, again, underdetermination is the wrong way to describe that question, but it's not something I'm really going to engage with here. I'm often, I think, going to slip between talking about decoherent unitary quantum mechanics and just talking about Everettian quantum mechanics or the Everett interpretation, but I want to flag that I'm not in this case defending that thesis, I'm just using it for simplicity. So the underdetermination here we're interested in is underdetermination between uncontentiously different theories with different formalism and different equations. Okay, so I cashed out a strong and a weak notion of underdetermination. And let's see if either of those notions of underdetermination is applicable to this question of this notion of underdetermination. Okay, so let's start with the strong underdetermination idea. And certainly a lot of the literature seems to have this in mind. A lot of the literature seems to have in mind that empirical data just is and forever will be silent on the question of which of, whether certain modifications of quantum mechanics are correct or whether unitary quantum mechanics is correct. So this is reprising the Dennis Dietz quote from earlier. To sum up, the different interpretations of quantum mechanics that we've sketched can be taken to be empirically equivalent in a strong sense. No future macroscopic observations can be expected to distinguish between them. So that seems fairly straightforwardly to be a statement of the strong underdetermination thesis with respect to quantum mechanics. I should say that Dietz is kind of hedging slightly because he has in mind that in principle there might be empirical tests of collapse theories, but he thinks that we'll always be able to modify the parameters of those theories so as to keep the collapse viable and just push it further and further away from what our experiments can get at. There's a whole other conversation about testability of collapse claims that we might be able to have in the discussion, but it's not something I'll focus on here. Okay, what's wrong with strong underdetermination? what it fails to get at is the scientific limitations, the limitations of success as scientific research programs of either dynamical collapse or hidden variable approaches to quantum mechanics. You might call these limitations of the modificatory way. And the limitation is basically this. There are no fully worked out versions of dynamical collapse theories or hidden variable theories or any other modifications of quantum mechanics that are applicable to realistic, interacting quantum field theories. So here's a helpful way to think about it. Quantum mechanics is really as much an abstract framework for writing scientific theories, writing quantum theories down as it is a specific concrete theory. There's a certain sense in which talking about the ontology of quantum mechanics, say, is a category error. Specific instances of quantum mechanics include things like, qubit spin networks and spin degrees of freedom of particles in ion traps and spinless particles moving at non-relativistic speed and electrons moving at non-relativistic speed and quantum superfluids and the quantized electromagnetic field and the quantized electromagnetic field as it interacts with matter and the standard model of particle physics and the various special cases of it, and arguably even the low energy limit of quantum gravity and potentially a quantum gravity we don't have yet. There would be a full version. All of these are quantum theories. They all fit the general unitary dynamics, Hilbert space representation, observable algebra structure of the abstract quantum theory. And the Everett interpretation is a recipe for interpreting these things. It tells us for each of these, this is how you make sense of it. This is how you connect it to apparent definiteness in empirical outcomes. But the general decoherent way of doing quantum mechanics covers all of this stuff, and it covers all of the relations between these things. It's large enough to encompass, for instance, the extent to which you might get non-relativistic quantum mechanics out as an appropriate limit of QED. The modificatory strategies we have basically aren't like that. They take specific quantum theories and they modify those theories. They add hidden variables or dynamical collapse laws to specific quantum theories. And in particular, they pretty much invariably take the quantum mechanics of non-relativistic particles and apply it to that. There's a literature that tries to extend these ideas a little bit further. There are collapse theories that apply to non-interacting particles in the relativistic domain. There are sketches towards relativistic field theories, but I think by fairly general consent, there's no version of this kind that's developed to, for instance, the level at which you can make sense of a QED calculation to one loop order. And furthermore, there's a reason for that. Or rather, there are general reasons for that. There are reasons to think that producing any such theory is going to be really difficult. It's not just a specific lack of imagination so far in doing it. And here's the reason why that, his basic reason why that is. There's sort of two components of a modification of quantum mechanics, or two halves of what it wants to do. Firstly, to fill the general requirement of these modifications to be a sharply formulated physical theory, then the modification needs to be stated in terms of the sort of microphysical, exact, sharp description of the theory. But secondly, the success condition for the theory is that the macroscopic degrees of freedom of the theory, the things that are supposed to be macroscopically definite, do in fact come out as macroscopically definite. So the way this plays out in a modification of non-relativistic quantum mechanics is that the theory at the fundamental level is formulated, or at any rate can be formulated, in terms of the position of individual particles. And furthermore, the macro level content is also formulated in the level of the positions of individual particles, or coarse grains thereof. So the way the theory is set up, it allows you to have a fairly direct line from the microphysical description of the theory to the observational description of the theory. Quantum field theory isn't like that at all. In quantum field theory, there is a highly indirect relation between the description of the microphysical level and the description of the macroscopic phenomenological level. In fact, I don't think it's a big exaggeration to say that the understanding that that's what's going on in quantum field theories has been the central aspect of understanding how quantum field theories work in in particle physics and condensed matter physics in the last 50 years. Quantum field theories are effective field theories. They're descriptions of the world at a certain level of description. They contain inside themselves the machinery and formalism to relate descriptions at one level to descriptions at another level. Those relations are highly dynamical and complex, and they have the consequence that the macroscopic degrees of freedom in the theory are related by a very messy, complex dynamical process to the microscopic degrees of freedom in the theory. Which has the corollary that if you try to write down a modification of quantum theory that chooses variables that are natural at the micro level, you've just got no guarantee at all that that's going to give you a description of the theory in terms of variables that are natural at the macro level. And the whole of the kind of machinery of renormalization and our understanding of how to tame the infinities and the kind of judo trick by which we turn the mathematical pathologies of quantum field theory into a deeper understanding of it, all of that stuff relies on this kind of stuff. So claim, which I can't tell you enough in this lecture about quantum field theory to substantiate more than I've done, claim not only don't we have relativistic field theoretic extensions of dynamical collapse or hidden variable theories that are satisfactory, that's not just a minor thing. It's a relatively deep issue in the way these things are put together. But closing brackets on why this is, here's just a flat-footed statement. The decoherent way of doing quantum mechanics can explain and describe all the phenomena that relativistic quantum field theory handles. And the dynamical collapse theories and hidden variable theories we have can't do that. If that's the case, I submit, it can't possibly be true that there's underdetermination between them. It can't possibly be true that only extra empirical virtues speak to which of these is correct. There's a ton of empirical data that one of these theories can handle and the others can't. So, in discussion of this, when you make this point, you often hear the idea that, okay, there's not, in that sense, underdetermination, but there is strong underdetermination between Everettian quantum mechanics and these other approaches when we confine our attention to the non-relativistic issue. So his calendar, at least getting close to this kind of claim, although it's hard to find it in print rather than conversation, confined to non-relativistic quantum mechanics, experimentally, there's no way to confirm one theory over another. All right. Let's for the moment stipulate that's true. Spoiler alert, it's not. But let's stipulate for the moment that it's true. It still makes no sense to run the thesis of strong underdetermination with the additional restriction to a domain. I mean, if you're allowed to do this, there is strong underdetermination between the general theory of relativity and Newtonian gravity. Because if you confine, you're confined to non-relativistic gravitational phenomena, experimentally, there is no way to confirm general relativity over Newtonian mechanics. Come to that, confined to classical phenomena, there is no way to confirm quantum theory over classical theory. So there is underdetermination between quantum theory and classical theory. This, I submit, is ridiculous. So I don't think there's any remotely reasonable claim of strong underdetermination that we can make in this story. Okay, so more prima facie plausibly, we might be able to make a claim of weak underdetermination. And indeed, the most careful statements of the underdetermination claim I know have this form. So here's calendar again. A clearer picture is painted by conceiving these interpretations as different Lakatosian research programs. And again, people who've done philosophy of science will recognize a lot of the ideas here. A research program is a series of theories sharing a hard core of temporarily unimpeachable theoretical posits. Quantum mechanics is a live theory, one being extended to new forms and realms. The non-relativistic theory of 1925 is applied to new systems daily, from ever more sophisticated treatments of helium to the recent discovery of non-equilibrium time crystals. The theoretical structure was also transformed into QED, QCD, and the Standard Model, and we hope to integrate cosmology and gravity with the world. So Callender applying these ideas to the underdetermination thesis is saying, okay, there's a GRW research program, or a dynamical collapse research program. There's a hidden variables research program, and there's a Everett-style quantum mechanics research program. And these research programs have various kinds of strengths and weaknesses, which we can trade off in looking which one seems to be doing better. And yes, absolutely, Callender concedes it's a strength of the Everett-style research program that it handles relativistic phenomena. But we've still got a big core of phenomena handled in all of these, and the Everettian program has its other weaknesses. And so, sure, we don't know how successful it will be to extend these programs in various directions, but that's just what goes on in a live scientific controversy. It's always the case in these controversies that there are some phenomena that some programs can't explain so well, but they say we're going to later, and they can appeal to other advantages they have to say this is why we think this program is ultimately the one that's going to succeed. And Calvin wants to say this is the notion of underdetermination that's applicable to the quantum measurement problem. Okay, so let's explore that. So I think what we need to explore to see whether that's viable is we really need to pin down what is this kind of supposed core where we actually do have significant empirical confirmation of these theories to say these are viable research programs that have done a ton of science, even though there's a ton more to do. And if that area was just, if basically that core was everything that doesn't involve, particles moving at relativistic velocities and the exotica of CERN and the LHC, you can kind of see how it goes. But it's kind of smaller than that. There are quite a lot of observational phenomena inside the mundane realm of what we ordinarily call everyday quantum mechanics that I don't think the dynamical collapse or hidden variable theories have the resources to handle. Okay, so here is an example. Here's some relatively straightforward observational evidence. The sky is blue. I appreciate that giving this talk in the UK, then the colour of the sky probably looks more like a sort of theoretical posit than a directly observable framework. But I took this photo in Santa Monica and the sky is definitely blue. Why is the sky blue? I have a 5-year-old, it's important you know the answer. The sky is blue because of Rayleigh scattering of the light from the sun off the molecules of the atmosphere. Rayleigh scattering is at the classical level is the scattering theory you get when you've got electromagnetic radiation scattering off an electric dipole where the relevant scales of the dipole are really small compared to the wavelength of the scattering. You can kind of treat it in classical mechanics, but to treat it properly, of course, atoms are not actually classical dipoles. So a properly quantum mechanical treatment involves you working out, using non-relativistic quantum mechanics, various matrix elements of the structure of the atoms, and then plugging that in either to a sort of semi-classical description of light, or if you want to do it carefully, to quantum field theory. But we can't do that in Bohm's theory, and we can't do it in a dynamical collapse theory, because quantum electrodynamics is not within the scope of those theories. Quantum field theory is not just for the esoterica of CERN. Quantum field theory is what we need to understand the scattering of light in the sky. Nor can we say that we'll just apply the quantum mechanics to understand the structure of the atoms and then hand over to some vaguely classical description that might be hoped to come downstream of the resources we're using to solve the measurement problem. Because the thing we're using quantum mechanics to do is to calculate matrix elements of operators in this framework. And insofar as we've got some additional resource, something added to the formalism in these modified theories, those additions are not usually tracking things of this kind. So to be vivid in Bohm's theory, for instance, the position of the actual electrons sitting in the electron cloud of a nitrogen molecule in the upper atmosphere, those Bohmian facts aren't the thing that we're plugging into our observational claim. That observational claim about coupling to frequencies of light is tracking dynamical features of the quantum state of the system, not tracking those Bohmian particles. Okay. One example doesn't prove anything. Here's another example. Think about the spectral lines of substances. Think of it, this is like the classic example you use when you're doing calculational work in an undergraduate quantum course. You do your undergrad quantum course and you're going to get at the deep mysteries of nature, and you find actually what you're spending most of your time calculating for perfectly good reasons is spectral structure of the atoms, and what you're connecting to observationally experimentally tends to be a lot of information about spectral gaps. So classically, standardly, in solving for hydrogen, for instance, you'll run through a series of perturbation theories working out the spectrum of hydrogen. and then you'll convert that to information about frequencies. How do you convert it to information about frequencies? Well, at undergraduate level, you appeal to the fact that E equals h bar omega. Again, that's not available in a Bohmian or dynamical collapse version of quantum mechanics because that's a piece of relativistic quantum field theory. If you want to do it more carefully, you actually need a story about photons and you need QED. But even if you're willing to kind of hand wave in the direction of these fragmentary things, these are not fragments of classical physics. They're fragments of a quantum electrodynamical theory. Non-relativistic quantum mechanics, if you like, is being used as a tool here to calculate what the energy levels are. The calculation is all being filtered through non-relativistic quantum mechanics, but the route from the calculation to the observation isn't. It needs to make use of concepts coming from outside non-relativistic quantum mechanics from elsewhere in quantum physics. Let's try one more example. Here's a sort of historically reasonably important example of the application of quantum mechanics. Think about the two-slit experiment. Well, the two-slit experiment is done with photons. And again, those are not within the descriptive capacities of non-relativistic quantum mechanics. All right, but you can do the two-slit experiment, or you can do other interferometry experiments with neutrons, can't you? Neutrons are moving, so the neutrons in a neutron interferometer are moving about 1,000 meters per second. That's fast as speeding tickets go, but it's not relativistic. Doing non-relativistic quantum mechanics to analyze neutron interferometry is fun. But how do you detect the neutrons? Neutron detection normally, at least, is a radioactive process. A classic example of a neutron detection is that you hit the neutron into some source that causes excitations or fissions or whatever, and then you pick up a decay product. It's perfectly well understood physics. It's calculationally hard work. Most of it we still understand to this day in broad, fairly qualitative terms, but the description of it inside quantum physics is fun. You don't have a description of it at all inside Bohm's theory or invariant theories, because at the risk of tedium, they're describing non-relativistic quantum mechanics, and radiative decay is not one of those processes. So we can't understand the two-slit experiment with photons inside the domain of Bohm or GRW, and we can't do it with neutrons either. I actually tried and failed in my sort of last-minute prep for this to work out how electron detection works, and it strikes me as shakily possible that parts of the detection of electrons can be covered to some degree by these theories. Although the preparation of electrons seems to be by shining, in modern experiments, seems to be by shining intense lasers on sources and causing them to give off electrons, and lasers are a quantum, sorry, this is getting boring, but lasers are a quantum electrodynamical phenomenon not within the regime of non-relativistic quantum mechanics. I mean, there's a sense in which I can't believe I'm giving this talk. I could just be saying that these things only cover non-relativistic phenomena, and that's a tiny chunk of quantum mechanics. And you just have repeated that 500 times. But there's probably a need for a bit more care. Let's spell this out a bit more, actually, and see the sense in which we aren't using non-relativistic quantum mechanics in these calculations, and how that sense is not enough for the dynamical collapse or hidden variable theories to really get some traction. So here's the kind of model of what quantum mechanics would need to be like, or what these actual experiments would need to be like, for the kind of here's how we solve the measurement problem story that's being told in dynamical collapse or hidden variable theories to work. We'd have to have something like, well, there's non-relativistic quantum mechanics, and from non-relativistic quantum mechanics alone, I derive some observations. That would have to be the model that was going on. And if that was the model that was going on, then the kind of, and this is perhaps a more naturally speaking to Bohm or to the primitive-ontology versions of GRW, for those of you who know this literature, but it broadly works wherever. The additional thing we're adding to the non-relativistic quantum mechanics can then give the definite observations that we need to solve the measurement problem. If we have this fairly direct route that takes us from the domain described by non-relativistic quantum mechanics to observation, then you can see how adding additional resources to non-relativistic quantum mechanics gives you the resources to solve the measurement problem by telling us how we model definite observations in our fields. But the real story looks like this. We have our application of non-relativistic quantum mechanics, whether that's to the dipole moments of nitrogen, or the spectral line of sodium, or the behavior of neutrons in an interferometer. Then we couple it to some other stuff, various bits of electromagnetic phenomena that non-relativistic quantum mechanics doesn't cover, and that we might model semi-classically or in all sorts of phenomenological ways, but which is still a physical complex process that's set from observation, and then we look at it. And so what we need from non-relativistic quantum mechanics is effectively certain outputs that we then plug into our other pieces of physics. So the outputs are very theory-laden things. They're matrix elements of various sorts, or energy separations, or frequencies of oscillations, or things of this nature. They're not things that are describable in ordinary observational language at all. And that being the case, the additional ontology we're adding has nowhere to go. It's not doing any work here. And again, this is particularly vivid if you have something like a primitive ontology view of something like Bohm's theory. So in a primitive ontology view of Bohm's theory, then what the theory is really about is the movement of the Bohmian particles. The quantum state is just there to guide where the particles go. Sometimes the quantum state is diminished to the status of a law. Sometimes it's you even attempt to eliminate it altogether in your metaphysics. And the particles are what we see, the particles are what the everyday world is. But what we need to actually analyze a concrete experiment in quantum mechanics is not the output of those particles. It's an output of a whole bunch of other stuff that uses the full representational capacity of the quantum theory. We need in understanding the color of the sky, we need the dipole matrix elements of the nitrogen molecule. We don't need the locations of Bohmian particles. Passing those to our additional theory is useless. And passing only those to our additional theory doesn't allow us to make a prediction. Okay, so there are more ways of being a modified quantum mechanics advocate than having a primitive ontology. You could say, okay, fine. We better understand there's a lot of representational work being done by these various bits of non-relativistic quantum mechanics. But look, isn't all of that common between these theories? So can't you get a sort of underdetermination thesis that says, well, what we're really using in quantum mechanics in these various applications of non-relativistic quantum mechanics is just a common core of all these frameworks. You know, Bohm has the quantum dynamics in it. GRW dynamical collapse doesn't happen in the scales we're looking at to understand scattering of light in the atmosphere. Don't we have some common content there? And isn't that doing all the work? And then you could have an underdetermination thesis about Everett versus Bohm versus GRW as to how you extend that common core. And people like Alberto Cordero and Matthias Egg have kind of advocated this sort of framework. But the problem is, insofar as you have a common core here, it's common because it's not solving the measurement problem. It's not, precisely because it's not in the regime of macroscopic superpositions that triggers the significance of Bohmian particles or the significance of the dynamical collapse mechanism, then this isn't a space where you can see if you're solving the measurement problem. In the Everett interpretation, or again, being a bit more neutral in unitary decoherence-based quantum mechanics with no modifications, I can expand that box. I don't need to confine my attention to modeling the non-relativistic phenomenon. I can model the QED. I can model, with admittedly plenty of mathematical approximations and shortcuts, the nuclear process by which the neutrons are detected. I can model all of the physics, including the physics which is salient to the measurement problem. I can model the creation of macroscopic superpositions and the analysis of how we should think about those. That's what the machinery in the GRW and Bohm theory is supposed to be helping us with. And they simply don't extend to that regime of application. Now, in that line, let me sort of loop back to Calendar's original setup of the problem, that we had a sort of common core of material that all of these theories can understand, and then various factors might mitigate in favor of one or other of these, depending on your various extra empirical preferences. So here's another Calendar quote. Calendar says, "The Everettian programs are minimalist one, little more than the quantum formalism itself, coupled to a new rule for reinterpreting our definite empirical outcomes. So it's little wonder that it can be successfully applied to physics. To someone engaged in a competing research program, trumpeting Everett's easy application to new physics sounds like a thief bragging about how little they had to work for their reward." But here's the thing. The underdetermination we have here isn't per se underdetermination between the Everett interpretation and Bohm's or GRW's theory. It's a supposed underdetermination between the quantum theory that is the jewel in the crown of 21st century science and this other program that's trying to replicate what it can do. So no wonder, of course, if your approach to interpreting quantum mechanics says, given that 20th and 21st century physics seems to have been kind of successful empirically, it might be a good idea to understand how it does that rather than trying to replace it with something else. Obviously, that research program is going to do a lot better at actually carrying out that task. But in any case, to loop back now to the weak underdetermination thesis, I'm suggesting that the core of quantum mechanical situations that dynamical collapse or hidden variable theories can actually give us an analysis of, all the way to observation, is much smaller than people think it is. It's very small indeed. I'm not convinced anything is in it at all. At the very least, extremely large classes of our terribly standard applications of quantum mechanics are not in that space. And incidentally, I think part of the problem I had in trying to find, to identify any example you could model entirely in tight and non-relativistic quantum mechanics is scientifically, it's an incredibly boring question. Why would we want to know whether this is a particular situation in which we can get away with doing it using a certain particular version of a Coulombic story about electrostatics, given we've got a perfectly satisfactory quantum mechanical understanding of electrodynamics? And that itself, I think, is kind of telling. But in any case, if anything can be modeled inside the physics of GRW and Bohm all the way to observation, I don't know what it is, and it's at least very small. So is that weak underdetermination? I mean, there's a research project. There isn't, in the relevant sense, a sharp refutation. In a sense, there can't be, because there's not a regime rich enough to make predictions. It's being done. People are doing it. In that kind of minimal sense, you could say it's a sort of underdetermination. But you could say the same about the steady state approach to cosmology, if that was our only approach to underdetermination. The simple existence of a research program that is being run by some people, seen from outside that research program, can't really tell you that there's scientific underdetermination in a serious way. People are still writing papers advocating the steady state theory of cosmology. Here's one from 15 years ago, but not that long ago, from somebody in the very small group of people working on these kind of ideas. Research programs in science can survive in small forms for a very long time. That's not to say, incidentally, that I think it's not to say that I think it's necessarily bad for science that these things exist. And it's certainly not to say that I think there can be no reasons to be advocating something like the de Broglie-Bohm theory that are any better than the reasons for advocating the steady state framework. Internal to the de Broglie-Bohm program, there's a perfectly sound reason to continue that program, and that is that they think the Everett way of understanding quantum mechanics does not work. They think there is no way to make sense of unitary unmodified quantum mechanics. And if there's no way to make sense of unitary unmodified quantum mechanics, then sure, try to develop an alternative to it. But underdetermination isn't that kind of thesis. And that's not an underdetermination thesis in itself. That would be a thesis that says, actually, you can't use and interpret the unitary theory at all. Underdetermination thesis is the kind of thing that you can have stepping outside the particular programs, where you'd say simply from the presence of these programs, there's underdetermination. I don't think that can possibly be maintained as a case of scientific underdetermination in these cases. All right, let me wrap up. Just to summarize. Most, for all I know, all of non-relativistic quantum mechanics can't be reproduced by any modification of quantum mechanics. In particular, the space of concrete empirical quantum phenomena in which modifications of quantum mechanics actually solve the measurement problem, actually tell us how to handle macroscopic superpositions in actual concrete experiments you can do on the table in the lab. That space is small at best. I strongly suspect there's nothing in it at all. So the measurement problem is not in any meaningful sense a case of underdetermination theory by evidence, and any attempt, therefore, to use the broader resources of the philosophy or the metaphysics of science to resolve it as a case of underdetermination theory by evidence is misconceived. And any lessons being drawn from it about how to think about underdetermination in general, or scientific realism in general, are likewise misconceived. And the argument, if any, for modifying quantum mechanics is going to have to rely on the supposed impossibility of solving the measurement problem within unitary quantum mechanics, and not on any sort of expected undesirability of any admittedly successful way of doing it. So I could pretty much finish there, but let me just as sort of epilogue, I have talked a lot about philosophers' response to underdetermination, but I mentioned also there's a physicist's response to underdetermination. And I think, insofar as it's the case, as I think, and as actually a lot of the participants in this debate think, that insofar as we can make sense of unitary quantum mechanics at all, it's only a la Everett, then really the shut up and calculate slogan says something slightly different from what it's normally said to do. I'll stop there.